Hey, George, you're a scientist.
I'm a chemist, yes.
Yeah, right. You're a scientist. So, why don't oil and water actually mix? Like, I know there's like the colloquialism, like, oh, they mix like oil and water, and like some things, like if you put like a lot of sugar into tea, like it'll kind of collect on the bottom, like it didn't all dissolve. So, like, I guess some things mix at like different rates, or they have like different saturations, but like then other things just don't mix at all. Like, why not at all?
Well, darn it, Lions. I am a chemist, not a fluid dynamics expert. But with my very limited knowledge and very limited area of expertise, I will attempt to opine to this matter. This does actually drift dangerously close to chemistry, but as long as I say it's something else, I don't have to be held accountable for not knowing my career field.
There you go. Plus, fluid dynamics sounds super cool.
I know, right? It's definitely one of those where there's a department of that in like the military somewhere, right? You know, where it's just like, oh, well, I'm a doctorate in fluid dynamics. And it's like, nice. What do you do? It's like, I look at planes. So let's start top of the hour because I'm going to, of course, approach this from a chemistry lens. Do you know the different types of chemical bonds?
No, I can think of something that might be related to what you're describing. There's a
bank bond.
Yeah, there's bank bonds.
James Bond.
There, yep. Yes. In fact, there was a big problem with who is going to be the new James Bond. So, like, we're still inventing new chemistry, it sounds like.
Yeah. like, do you know your Bonds? Well, there's Pierce and Sean.
Yeah, Roger Moore, who doesn't get the credit he deserves.
Yeah, right.
So, I want to say, like, I know the word covalent, like from way back. I can't not tell you what that means.
But you just like dusted that off from like you opened the door that said 10th grade chemistry, and in there was a box that just said covalent, and you're like, this is a thing, right?
Yes. Yeah. Somewhere my high school chemistry teacher just went like, got like a little thrill. He doesn't know why, but one of his students remembered a chemistry thing.
There you go. Well, covalent is one of them. So nicely done. The four big ones is covalent, ionic, hydrogen, and metallic, right?
Hydrogen gets its own type?
It does.
All those elements, and that one gets its own type.
Hydrogen is like so uniquely weird, man. You know, like there's even arguments on where it is on the periodic table, you know? Like, so is
it the first one?
It's the first one. Because that's the thing, is that it's the first one, right? So like it's a proton and electron, but sometimes it's just a proton, right? And it's so critical in the way that it works. And we will talk a little bit about hydrogen bonding today. But the two that we're going to talk the most about is covalent bonding and, covalent bonding mostly, actually, but to touch on like covalent and ionic bonding, right? So ionic bonding is like you had an electron and I had an electron, right? And I take your electron. So can you think of some things that might be ionically bonded?
So it would, now you have like multiple molecules and not enough electrons to go around, so it's something charged.
Atoms, typically.
Sorry, multiple atoms. But if they're sharing electrons now, does it have a charge to it?
Well, so they specifically don't share, they steal.
Oh.
And so that's, yeah. It's like you had an electron.
Right, and now you have, okay.
Yeah. That's not the end of the movie where they decide to share all of the oil.
and
if I remember
then
correctly.
They all got milkshakes. it's like the edited for seniors cut on The Simpsons.
I was picturing like you're watching it with like your 8-year-old and you pause it and you're like, and then they all got milkshakes and like, the end.
Really? That was so sudden. Go to bed. No, I can't, but I'm sure this is going to be one of those things that like, as soon as you start naming things, it'll be like, right.
Oh yeah. The thing, salts are the easiest one. Actually, I believe that all salts are definitionally ionically bonded, right? So sodium chloride, right? You know, that's an ionic bond. And one of the cool things about sodium chloride is that like, so it's made up in like a lattice where you have like positive, negative, positive, negative, positive, negative, and it's in this huge lattice structure, which is why if you hit it with a hammer, it just shatters and it's so brittle. Because when you hit it with your hammer, you force all of those off, and then all of a sudden negatives lined up with negative and it repels and kind of blows apart, right?
Yeah, that's kind of fun. So like at the atomic level, they're separating the same way we kind of see like on the macro level.
Yes. Yep. Exactly. Right. So those are ionic bonds. But basically, the idea is that like sodium straight up gives up an electron, chlorine takes that electron, and so now sodium's happy because it has, like it's at its lowest energy. Right. It's not an octet, but it's got only its 2s orbital filled. Right. And then the chlorine's happy because it's satisfied the octet rule. So like everybody's happy. Right.
Is this why when you see salt written out, it's like NaCl plus?
It was Na plus Cl minus.
That.
Yes. And so when you put it into water, right, the water just dissolves it, right, into Na plus and Cl minus, and they both kind of like go around, right? With covalent bonding, there is actually sharing of electrons, right? So, the idea is that it's like, hey, man, like carbon says to carbon, like, hey, man, I got 4 electrons, right? And other carbon says like, well, I got 4 electrons. It's like, well, what if we were to share an electron, right? Or share 2 electrons? It's like, oh, well, then we kind of both have 5 between the 2 of us, right? And then eventually they get a few more people involved in this pyramid scheme, and all of a sudden they've got 8 electrons, and everybody's happy, right?
If you get 2 friends who have electrons, and then they get 2 friends that have electrons, it's nice to know that the small world is sometimes as simple as the big one.
Yeah, and actually that's very much so how making plastics work. And if you'd like to know more about that, we have an episode about recycling plastics. But yes, plastics are effectively the pyramid scheme of like, well, okay, you get, you get a molecule and then get 2 more molecules. That should be the tagline for plastics, the pyramid scheme of chemicals. So just like with any good pyramid scheme, covalent bonding, the sharing isn't typically equal, right? So like if it's, in a perfectly equal world, right? Like, so imagine you've got, 2 atoms, right? And they're sharing electrons, right? Then the electron cloud around them would be completely evenly distributed, right? And so they would effectively have no charge, right? So that's great, right? But some atoms are big giant electron hogs, right? And interestingly, as you go to the right and up on the periodic table, you increase what's called electronegativity. So that means they are bigger electron hogs, right? So, So that's
is that like that sounds like an obnoxious like positive negative electrical engineering thing. So increasing the negativity means they take more electrons.
Yeah, well, so more because electrons are negative. So this one actually makes sense.
Yeah, it's
right?
Negative charge, right?
Right. So electronegativity is like there's more electrons giving us negativity, right? That one makes sense to me. It's not like because that's the problem with electric charge is it's just like, okay, the charge is going this way to the right because the electrons are going in the opposite direction. And you're like, that's so uncomfortable, And yeah, so it's just I remember learning that and being like, why? And then being like, well, it's not that big of a deal. It's just remember that the charge goes in this direction. I'm like, but that's the opposite that the electrons are going. And they're like, oh, you're a chemistry major. And I'm like, I am. And they're like, yeah, this is gonna stink for you because but basically is what electronegativity does is it again creates electron hogs, right? So imagine you've got like carbon. So carbon bonded with carbon, they're both equally electronegative, right? So they share pretty nice and pretty evenly. But when you bond carbon to like an oxygen, the oxygen tends to hog some of the electrons. So it gives you what's called a dipole moment or a slight negative charge on the oxygen and a slight positive charge on the carbon, right? So what that means is that they're no longer like uncharged, right? So a great example of this is water, right? So you take, as we were saying, hydrogen, the best one,
Weird,
and an oxygen, and an oxygen. So like hydrogen's got a single proton that is trying to hold on to its share of the electrons, and now you've got oxygen with its 16, nuclear weight, right? Right? It's got 16. It's got an atomic mass of 16. Forget 8. It's have 8 protons. Anyways, no, that can't be right. It doesn't matter. No, wait, that's right. That's right. I'm not staring at a periodic table. That's literally at one point I was giving somebody a tour of the lab and they were like, oh man, you got so many cool periodic tables. Are they there for decoration? I'm like, no, we use them. Like
science.
Yeah, like they're not there for showing, they're there for blowing. Anyway, so the oxygen is much bigger and more electronegative, so it hogs all of those electrons. So now what you've got is, imagine a water, right? You've got the oxygen that is a little negative, fairly negative, and the hydrogens that are fairly positive, right? Which means now if you put a whole bunch of those together, what happens is the negative oxygen aligns with other positive hydrogens in water, right? And they kind of form like this kind of lattice structure, right? And they like aligning themselves that way. So does all that kind of make sense?
Is this why water has surface tension? Because they're like
yes,
kind of sticky.
Yep, and why oil doesn't in particular.
Yep. It's all coming back.
Yeah, I love it when a plan comes together, right? And also, too, why water in particular expands when it freezes, because all of those are suddenly locked into place, and they're not allowed to kind of move around each other, so they expand a little bit as they lock into their lattice structure. And why snowflakes look pretty and all that kind of good stuff, right? With all of that in mind, right, let's take a step back for a second and talk about what are organics?
Living stuff.
You'd think that, wouldn't you?
I think specific, like in science terms, I think it's specifically like things that are only like made out of some of the elements, right? So like I think metals are inorganic.
Mm-hmm. Metals are inorganic. Yep.
Yeah.
Yep.
So
you're gonna get there by like process of elimination.
Yes, I will.
You got a huge periodic table.
Plutonium, I think, is inorganic, right? So like it's
a metal.
Yeah. Plutonium counts as a metal?
Absolutely, it does.
Gross.
Yeah. Take that, plutonium.
Well, that made me suddenly think of like normal metal things, but then made out of plutonium. Like I have plutonium cookware, and like the stand on my monitor is plutonium.
Well, I mean, that's kind of why they have depleted uranium, shells and bullets, right? Is because it's a metal and it's way denser and heavier than most other metals. So they're like, okay, well, we depleted it, so it's not, like the high level radioactive, and it hits real hard. But yeah, no, it's most things on the periodic table are metals, which is kind of weird to think about.
Huh. Okay, so
but most things aren't metals.
Yes, but most of the materials we have for making things are metals.
Yeah, like most of the categories, like if you were to say like each bucket is like an atom, right? It's most of the buckets are metals. There's just fewer things in the buckets than we have for non-metals, right? It's like, here's all the buckets for the metals, and here's the dump truck of carbon that we have to deal with,
So that was going to be my big swing, is that organics have to be made of carbon.
Yes, you got it. Yeah.
Yes.
Got it in 3.
Organic life.
Yep, exactly.
I've read science fiction.
Which is interesting because, and as I'm kind of jumping all over the place, is that they've actually made, if I remember correctly, ideas for like sulfur-based life.
I've played Masters of Orion.
Silicon-based life, because it's below carbon on the periodic table, so it would behave chemically similarly, but it can, because it's a level lower, it can do other like weird chemistry stuff that carbon can't do. And so it's just kind of like, well, what would that look like? I'm like, I don't know, but let's find out.
To the laboratory.
So I say all that to say that, so carbon-carbon bonds, right? That's what kind of defines organics, but it can be bonded to kind of anything, right? So broadly speaking, right, like carbon bonds for organics. Now, what you can do is you can have like the one extreme, which are called paraffins, right? And have you heard of paraffin before?
Yes, because of paraffin wax.
Exactly, right? Like that's the main thing that paraffin? Do you mean paraffin wax? I do. So paraffins are basically long hydrocarbon chains, right? So it's just carbon, 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 and everything branching off of it is hydrogen, right? So because of that, and because all of that is similarly electronegative, right? Is it just kind of, they're all groovy, man. They all share their electrons and everything's kind of cool, right? So when they run into other stuff, they don't tend to like align or, try to get into a certain order because of their electronegativity, right? When you start adding electronegative stuff on there, like oxygen, all of a sudden that screws everything up, right? So now the oxygen is hogging molecules, right? But the oxygen, so if you add, like, for example, a an OH group onto it, right? Now all of a sudden the oxygen is hogging all of those molecules, which means that it does no longer get along with its former organic brethren. It now thinks it's more like water, right? Because it's got that OH group on there and it's got that electronegative spot, right? So so that's kind of like where it will now start to drift towards water, and what kind of goes to your point of solubility, right? So oils, right, are typically long unbranched hydrocarbon chains, right? You know, because they're just fats and that sort of stuff, right? But water is H2O, and it's extremely electronegative, right? So that's why those two things is what the oil does is the oil says like, oh my God, this is way too intense with this, like, you know, electronegativity and unequal sharing of electrons, and then they all kind of bunch together and they basically try their best to get away from the water, right? As the water kind of pushes it all together. This leads to some like pretty neat stuff. And once you kind of know this in principle, it explains a whole bunch of different stuff. So for example, right, as you say, like oil and water don't mix, right? But you can't say organics and water don't mix because there are plenty of great examples of that. For example, can you think of a very famous organic molecule that mixes famously in water?
Sugar.
Sugar can, yeah, to a degree, and it's because it has a whole bunch of different OH groups on it. It's basically like a hexagon ring of organic, and it's got like OH, 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 and it just dissolves in water. It'll eventually become saturated in water to where, like, as we all learned when we were young kids, right, is that there is a limit to how much water you can dump, or how much sugar you can dump in the water before it just starts to pile up on the bottom, right?
Yes. Why does my Kool-Aid now look like a little mountain on the bottom of the glass?
Exactly. So that's what would be called soluble but not miscible, right? So like so I should have said miscible, which is to say that you can pour an infinite amount in there and it'll just keep on mixing, right? The most famous example of that is ethanol, which we use to poison ourselves. Right.
So wait. So if you mix ethanol and water, the way they chemically interact is different than adding like sugar or Kool-Aid mix to water, because the way the bonds happen is actually different between those two.
Well, so actually what it's doing is the same. It's interacting with the water in the same way in which is to say that the OH groups are the things that are interacting well with the water, right? And the carbon groups are the things that are not, right? But the thing is that, like, because of and this is where we're gonna start to hit the depth of my off the cuff understanding, right? Is due to both. It can be both the what's called the stereochemistry, so basically like where everything is on the molecule, and the percentage of oxygen to carbon, right? It's only able to do so much before the water's like, I've run out of ways to bridge the gap between all of this, and now I just can't put any more in me. Whereas ethanol, on the other hand, is just CH3, CH2, OH, right? So there's just two carbons and an OH, right? So that's why, like, there's not enough organics there for the water to start to try to kick anything out, right? So you can, mix, you can have a 50% mixture of ethanol, you can have a 100% mixture of ethanol, and there's never going to be any separation. The same thing with methanol, which is why, like, if I remember correctly, was it Everclear, right? That's like 180 proof.
Yeah, it's like 151, I think, in Everclear, or like in similar camps.
Yes, yeah, or 151, rum, right, which is 151 proof, which is 75.5% ethanol, right? So like you can have that kind of near infinite mixing. One of the other cool things that that these things can do, which I think is fascinating, right, is that what if you tried to do a two-phase situation, right? Where you actually tried to say, like, okay, I want an organic molecule and a water-soluble molecule, but I want them to be the same, right? That is something that you've used. You've used the two-phase molecule, right? You probably used it in the last week. You know what it is? Soap.
I hope more recent than the last week.
I'm just, I'm not here to shame,
No, I mean, it was as recently as Check's calendar.
Yeah, it's like, oh God, I gotta get my life together.
So that, like, because soap does like a weird thing where it like envelops stuff, doesn't it? Like, that is technically how it cleans. I remember reading that in like a fun fact thing at some point.
Yeah, so basically, is the stuff that's on you that you want to clean is ostensibly organic. It's the oils and dirt and all that kind of stuff, right? So what it does is it has a long hydrocarbon chain, like a long tail, right? It's normally like 10 to 18 carbons, right? It's basically oil. And then they said, yeah, but we're going to put something really electronegative on the end, like a carbonyl group or a sulfate, right? Which is why it's like sodium lauryl sulfate, right? Is a soap, right? It's literally telling you what the molecule is. That's one that you could draw from just the name, right? And so what happens is the long carbon chain says, oh my God, look, oil. And it goes and grabs it, right? And then the sulfate side says, oh my God, great, water, right? And so basically all of the tails all envelop the thing and then create this little ball, and then the water washes it away. And that is how that works. One of the other really cool things is the other place where you see a lot of this is in cell walls. So like, cell walls are based off of this concept, which is to say that they've got it's just two-sided, right? So the top side is water soluble, and then there's a fat, and then there's another molecule that's a fat and then water soluble, and that creates the cell membrane that allows it to differentiate itself from the universe, right? So oil and water not mixing is fundamental to life in its entirety.
Yeah, as we know it. Yeah, that's that makes me wonder, like, does every language on earth have some version of the like, oh, they go together like oil and water? And it's like, right, because it's innate to our very selves.
But the interesting thing about that is that, like, as you having that information, at one point I was talking to my mom, and she had some like wax that had really gotten into like this like kind of material, and she was just like, I can't get it out. I don't know what to do. And I just said, like, well, why don't you just soak it in oil for like 20 minutes? And she was like, will that work? And I'm like, well, yeah, because like attracts like, right? Because it's oil and a paraffin, so like it'll remove it. And it did. And she was like, how did you know that? And I was like, okay, well,
let me take you way back.
Yeah. And so I started with, I was like, well, they're both organic. Okay, wait, hang on. Here's what organic is. Okay, wait, hang on. Here's the periodic table. And then it was in that moment that I was like, oh, right, I did go to school for this. Like, it took them more than 20 minutes to give me the knowledge that I needed to make that assessment, right? But yeah, so that is why oil and water don't mix, is because one is non-electronegative and the other one is electronegative. And this goes into like, so this is like something that's just so fundamental to so many different things, because the more electronegative something is, the more intermolecular forces they are, which means typically the higher the boiling point, right? Which is why, like things that are more volatile tend to be more organic, right? Like propane, right? Versus like, so for example, if you take propane, right, and you were to get liquid propane and pour it onto the counter, right, it's going to like explosively vaporize, right?
At room temperature.
Yes,
right.
absolutely,
yeah.
right? Because it's a gas at room temperature, right?
I know, I'm just making sure.
Yeah. But then if you take ethanol, right, which is instead of an extra CH3, you just replace it with an OH, pour that on the counter, it will evaporate. It'll just take it a second. And if you pour water on the counter, it'll take quite some time to evaporate. And those are going in increasing levels of electronegativity. So you can kind of start to say like, oh, okay, well, like, well, what would be a better insulator? It's like, well, something that can absorb more energy before it starts to screw around. So it's like, well, like this would probably insulate better than this other thing. What would be better at carrying an electric charge? Well, something that's more electronegative, has the better ability to do that, which is why like things that are incredibly electronegative, like ions and salts, right, are really great at carrying an electric charge, which is why if you try to put an electric charge across water, it's not great. But if you throw some salt in there, it works like gangbusters,
So get out of the pool in a lightning storm.
Yes.
Emphatically, yes.
Emphatically, yes. I mean, to be fair, all of the extra, like chlorine and balancing they do would make sure that it killed you, which is good, right? Like, because you don't.
Like, I don't want to suffer.
Like, yeah, right. It's just going to be like, bam, done. Just like that one poor dude who was behind us on the mountain who was afraid of flying. And I tried to explain to him why, like, no, it's cool because like you'll just die. And you were like, dude, you need to stop. He's having a panic attack.
He's not cool about this at all. I am actually going to go stare at a lava lamp and think of another question I wanted to ask you about.